Okay, we're going to be talking today about how to do the density problems that you've been assigned. And you will have 2, maybe 3 more sheets that are the same size as what you have right now with just different numbers in them. I'm going to drill you to death on how to do the density, because that is the method of calculation that we're going to be using for the rest of the year. Now, if you look at the whiteboard right now, you're going to see, so this is what you see at the top of the chart, right? Example A, and I gave you the density for sulfur. For all the ones that you do as regular problems, you had to look up the density. Where did you look? What page? 914, good. 914, 15, and 16, depending on the element, right? Okay, so once you get this, my issue with most students is that they see this and don't realize that that's really a fraction. Or that you could think of it another way, it is a ratio. Full ratio. It's full ratio's ratio. Now, you got to get into this a little bit with me. It's important to have a little bit of fun, because chemistry can be pretty dry if we don't have a little bit of fun. So, I would like you to say it with me. Say it like this. Ratio. Okay. Oh, you're getting into it. Good spirit. I like that. 1, 2, 3. Ratio. One more time. Oh yeah, get that in there too. Why not? Here we go. 1, 2, 3. Ratio. Oh yes. Ah, you're into it. Okay, good. Now, yes, I'm certifiable. Okay, right here is a ratio. Ratios wind up being equalities. So any ratio can be written as an equality if there are different units of measure. Okay, so you have to have the units of measure in there or the equality doesn't work. And once you can write it as an equality, you can write it as a fraction, with either side on top. Because remember earlier we talked about if A equals B, what is A divided by B? 1. Because A and B are the same. If we have A over B, it's 1. What about B over A? It's 1. Sure, because both sides of that equality are the same thing. They don't look the same, do they? You look at that and you say, oh, wait a minute. 1 cubic centimeter is equal to 2.08 grams? Come on. Well, it is. In what way? It means that if I have 1 cubic centimeter of this stuff, it's going to weigh 2.08 grams. And if I have more than 1 cubic centimeter, it will be something that I can put into what you're going to see right now, what you've already been doing for the last several minutes as you worked in your groups. What I want you to do in all of these density type problems, I want you to always do the given and find. If you haven't been doing that, do it, or you won't get credit. Okay, so on letter A, and let's get some people into the act here, get you a little bit involved. And Diane, how about it? You get to go first. So Diane, what's given in example A? No, that is the ratio. What is the given amount? Ah, good. 13 what? Yes, 13 cubic centimeters. That little dude. And we are supposed to find whatever the other one is. So if we're given 13 cubic centimeters, they have to ask us for the grams. All right, so grams is what's going to be. Now comes the first fraction, and that goes to Angelo. Hey, Angelo, you're on. What is the first fraction going to look like?
So 2.08 grams per cubic centimeter. Over
Yes.
over 13.
Okay. Over what?
Over 13 cubic.
No.
Oh.
This is this ratio. Okay, I was pointing to this is this ratio. Okay, a ratio? Yeah. All right. So, we're not going to be putting the given on this fraction, ever. This is the ratio that we call density, which is a mass. How much mass equals how many cubic centimeters? Okay? All right. Now, what is the next fraction going to be, Gavin?
13 centimeters cubed over 1.
Perfect. Why do you have cubic centimeters on the top? Why not on the bottom?
Because it's not 1 over 13. It's just, there's nothing under it.
There's nothing under it, and we kind of ponied it up to look like a fraction, right? Because when you divide any number by 1, it's the same number, right? So we haven't changed anything. We just made it look like a fraction. Could I see a show of hands before you got to chemistry? How many never multiplied two fractions together? Anybody? Oh, so you know what to do. So how do you multiply two fractions together? Let's go to Armin. Armin's right here. And how about James? Okay, what if I had a number down here? What would I do with it? If I have a number on the bottom, what does that do? Let's say this was upside down. Now what would you do? Okay, it's down below. So how are you going to run this in your calculator? So what's the number you're going to put in your calculator first? Yes. And then you hit the divide sign, and then you put in the number, right? But in this guy, you're absolutely right. We just multiply across the top. Now, if you have a whole bunch of fractions, you multiply across the top, multiply across the bottom, divide the bottom into the top. Okay, that's how it works. And so, what's our number going to be? Ben? What do you say? Uh-huh. I think you're the only Ben in the class.
Oh, I need to calculate it.
Huh?
You multiply those two, right?
Uh-huh. You don't have a calculator?
I do.
Oh, good. Tell us what the number should be. 27.04. Okay. Let's look at it. 2704. Now, why did I mark it 27? Or why did I cut it down? Oh, wow. Yes, go for it. Nearest number to it, but why is there only 2 digits in this number? Go ahead, Ben.
You rounded it off?
Yes, why did you round to 2? Huh? Why did you round to 2? Why to the nearest 10th? This isn't to the nearest 10th, this is to the nearest ones unit. What do you think? What?
No, actually.
Okay, it's sig figs, folks. It's sig figs, significant figures. Sig figs say when you multiply 2 guys together, or divide 2 guys one by the other, the one with the smallest number of sig figs, and this is 2 sig figs, that limits your accuracy. It forces you to round this to 27. Okay? Now, if there was an 8 here, we would round this to 28. If there was a 6 here, we'd round it to 28. Yeah, okay, good. I realized the 8 might be a confusion, so I'm glad you all knew. That's wonderful. Okay, let's do the next one. And notice this is going to be different. For the sake of time and getting this to you, I want to go ahead and go straight through this without asking questions. Our given and find. We have 41.7 grams. We don't use the density. Okay? That's not a given in my calculation method. So, we've got the 41.7 grams of calcium, and we're supposed to find the cubic centimeters. Now, this is kind of weird for you, but it takes a little, after you get used to it, it won't look quite so weird. Because cubic centimeters is the find, and let's get my arrow back here. Okay, the cubic centimeters here is the find. The given is this. So the find determines that cubic centimeters here has to be on the top. Ben, I'd like your attention up here.
Okay.
Thank you. And so the other side of the equality, which for this particular element is 8.65 grams, is equal to 1 cubic centimeter, that's going to go on the bottom. Now look at this and compare it to this. Here, let's get the arrow up. And there we go. Notice grams is on top here, but down on the bottom one, the grams is on the bottom. And the simple difference is that in this guy, cubic centimeters was the find, and on the other guy, the find was the grams. Okay? Next thing we want to do is take the find and put that over 1, and that gives us this guy. I'm sorry, the given over 1. Have you noticed in all of your problems, the given is always over 1?
Yeah.
And the reason for that is the find is always putting the unit of measure from density that matches the find on the bottom. So it's always going to be that find, right? And that allows us to get the unit of measure for the find at the end. Isn't that cool? Unit cancellation. It works every time. Yes? I left it at 4.82 because there's 3 sig figs here and 3 sig here. There's 3 sig figs here and there's 3 sig figs here. So we are not limited. We don't have to cut anything down. And the one here is a definition. So it has infinite number of sig figs. It doesn't limit us. Okay? Are we good on that? All right. Yes, this goes in standard 4. We're going to be talking kind of the basics of scientific notation and what scientific notation is. So put this in standard 4 with a separate sheet of paper, and you will be glad that you had it. So our first little bit was scientific notation. Let me go ahead and put it up here. Standard 4. And the least number of digits that you could have in a number is 1 digit. And this digit is 3. It's not 0. And so it counts as scientific notation when we put a power of 10 with it. So the power of 10 in this particular case is 2. And if I were to write this number as a number that is not in scientific notation, let's see how this corresponds. Anybody can tell me what this number is going to be without 10? 300, absolutely. Now, would we put a decimal after that? No. Okay, if we did put a decimal after that, that could only be put there if we did this as the original. Oh, if we do this as the original number, then we're going to wind up having to put, I'm sorry, I confused myself here. If our original number is like this, to put this into scientific notation, we would have to go like this. 3.00 times 10 Now, how far do we have to move this guy over?
Two.
Or this guy over, I'm sorry. 2, okay? That goes with a positive number because positive powers of 10 move us to the right. That would be the scientific notation for 300 written this way. And this, okay, 300 written this way gives us scientific notation that looks like this. 300 written like, here, let's get this, there, okay. 300 written like this becomes this because, does everybody have their little rule sheet? Sig fig's the easy way? Yeah, good. Okay, you'll find on there, there's a rule that says trailing zeros never count. Our trailing zeros will count sometimes. I apologize. Trailing zeros count sometimes. And what does it take to make trailing zeros count? Anybody looking at their sheets? Yeah. Okay. No. No. That's not what makes them count. Trailing zeros. See, this 0 and this 0 are trailing zeros. As are this 0 and this 0. But these guys count. Why do they count? Because there's a decimal in the number. Okay? And the decimal could be anywhere, folks. Anywhere at all. The decimal could be here, here, or here. It wouldn't matter. Now there's no decimal in this number. So when we write this number in scientific notation, the 3 is all we need. In fact, if we wrote this 3.00, it would be incorrect. It would be giving us more accuracy than the original number had. Okay, this is only 2 sig figs because there's no decimal in the number. The trailing zeros don't count. Okay? Now, the other requirement for scientific notation is that a decimal if more than one number. So here's another example of a decimal, and let's go ahead and put this guy back. I think this was a 6. It doesn't really matter. It's just a power of 10. Okay? Now let's take some real examples. Here's some real examples over here on the left. Each of them is slightly different. But what about this guy? What is it? What does it look like?
Charge.
It looks like a number line. And you could have answered charge, of course, because in chemistry we have charges. And we will talk about those later. This would be a dipolar molecule. That's a little bit in the future here. But we'll be talking about dipoles. Dipoles make magnets. If we have plus and minus, it's just like on a battery. And if you run a battery through wire, if you have a wire that's connected to 2 ends of the battery and you run a coil around a piece of metal, you can magnetize the metal. Yeah. But this is just a number line, and the number line shows that the positive end of the number line is going to the right to increase. So if we start at 0, positive numbers will take us to the right, and negative numbers will take us to the left. I'm using this as a memory gimmick. Okay, you all know about number lines, don't you? Number lines are something that is so basic to mathematics. If you didn't know number lines, there'd be something really, really wrong. Okay, so let's go ahead and see how these powers of 10s are going to play out. So let's do the first little dude over here. Now, there's the number. I would like you to write down on your paper what you think the scientific notation should be for that number. Give it a shot. Just try it. See how you do. I'm gonna stop my recording. I want those of you at home watching this, I want you to stop the recording as soon as I do, and then try to write down that number for yourself. Okay, so here's the number the way it should be. If you stopped your recording, here it is. And this guy has the decimal here, and the power of 10 moves it 3 to the left, which gets us back to this number. Decimal here, 1, 2, 3 to the left, and we're back to the original. So let's go and look at a new one. There we go. Now this guy is going to be 21.50. And if we have 21.50, we want to write that in scientific notation. Would you all give that a shot? You probably saw it anyway, but that's okay. And we'll stop the recording and let you try it yourself at home as well. Here we go. Now let's see if you got it right. Yeah? 2.150. Now, why do we keep this 0? It's a trailing 0. Why do we count it? Not after there is a decimal period. It could be, the decimal could be before or after. That's important to understand. You'll see. No, then it's not scientific notation. What's the definition of scientific notation? The question was, could you write 2,150 to the power of -4? Right? -2. Yeah, right. Okay. -2. Then it's not scientific notation. And the reason for that is scientific notation is always going to be one digit, then the decimal, okay, like this, and then however many sig figs we have. Okay, and in this case, we had additional 2 numbers, which give us 3 significant figures, instead of this guy, where we have only 1 sig fig. Okay? And this could have been a 10 to the -6. Okay, this would have been 10 to the -6 if the decimal were originally out in front, which would give us let's see, we'd have 5 zeros. Yeah. 0.1234 and then a 3.1, or a 3, not point, the decimal's already there. That would be 325. Okay, so this would have been the original number. Now, why is it that these zeros don't count? Huh? No, not because there's more than one. Oh, wait a second. These would count. Because there's a decimal. Oh, no. No, it still wouldn't count. Why? What's the rule? So that makes these leading zeros, doesn't it? So these leading zeros would not count. And by the way, this assumes 10 to the -6, where this number assumes 10 to the -6, where this guy was 10 to the +6. So this is another example. And to write this one, it would be 3.25 times 10 to the -6, where this guy was 10 to the +6. So we would have 325 and 4 more zeros, right? So, number line, very, very important. Now let's go on down and let's look at the next dude on the right. Okay, would you all please write that in scientific notation? Yes?
If it's 10 to the power of 1, do you have to write power of 1?
Question. If it's 10 to the power of 1, do we have to write the power of 1? Only if we're doing scientific notation. Where would we have that? If this guy were a power of 1, right, would we have to write the 1? It would be a good idea. Not because it would be wrong, but because it makes it look more like scientific notation. Okay? Some power of 10. Okay. So, would you please write this number now, right here. And I will stop the recording. You should do that at home. So, let's look and see if you got it right. 10 to the 6th, right? Correct?
Yeah.
Yay. Now, we don't write the zeros because there's no decimal anywhere in the number. So, why do we have the power of 6? Because it's still got those the 5 zeros. The problem is that they're not sig figs. Okay? So, scientific notation, you have to take into account significant figures. So they you got to kind of learn both at the same time, which is what I'm trying to do with you now, instead of just giving you some straight examples. And we'll do examples of counting sig figs in numbers to help set those rules in just that'll be actually tomorrow. So we are okay. All right, let's write this guy. No, it's not. Looks the same, but it's not. It's very different. And we'll talk about it in just a minute. Go ahead and give it a shot. Okay, here we go. Check yourselves. Okay, why would you put -6? Okay, look, if you put a -6 here, that would make this number 0.50 and then the 4, I'm sorry.
I'm sorry, what did you put zeros?
You have to put the zeros because there's decimal here,
Okay.
and you can't put a decimal here, right? But there's a decimal here, which makes the trailing zeros count still. Okay? And so we're writing it a different way. In this particular case, writing it in scientific notation is no benefit, because you still have to write all the zeros. Writing this guy over here in scientific notation was really helpful, wasn't it? What if this were 23 zeros? You'd really be happy to have a 23 here instead of having to write 23 zeros, wouldn't you? Think about it. For those of you at home, I'm walking across the room. 1, 2, 3, 4, and I'm writing zeros in the air. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oops, I'm going to run into the wall, man. I'm out of space. Okay, it's a lot of zeros to write, yeah? Yeah, so we don't want to do that. So scientific notation is extremely helpful for dealing with really big numbers. Okay. And we have that with chemistry because you have to have a ton of not a ton, but you have to have a whole gazillion atoms just to be able to see the stuff. Okay? Because you can't see an atom. All right, let's go down and do I have another one down here? I do. Good. Okay. Let's go ahead and look at the last one. Here we go. Here's my number. Write that in scientific notation. And you at home, stop the recording, try it yourself. Okay, let's see how you did.
Yes.
There it is.
Yay.
Okay, 10 to the 1. Why do we include the 0? Trailing zeros count when? When there's a decimal. Right. Okay, so there's your 0. And 2.980 times 10 to the 1. We are right back to this number. Got it? Whoops. Here we go. Okay, 29.8. Write that in scientific notation. See, if there were no decimal in there, that would wind up being the same number, right? Okay, let's see if you did it. Yeah. Okay. Getting a little confidence here? A little. You're just getting exposed to it for the first time. If you want to get up on scientific notation, if you will look, actually sig figs, if you want to see how I work with this little page, and the page that I'm looking at is Counting Significant Figures the Easy Way, which can be located on my website just by doing a site search. And then you can also look it up in YouTube, and you will see it there. That's it for significant figures today. Let's see.